Hello everyone. Today we're going to learn about Docker and Apache Juneau Microservices. This course is mainly targeted towards Java developers who would like to learn about technologies used in the cloud space. Today there is a lot of buzz around Docker and application containerization in general. Running applications in containers instead of bare metal physical machines and virtual machines is gaining a lot of momentum and is considered one of the fastest growing technologies in the software industry. Microservices have also become increasingly popular over the past few years. Containerization, that is, running applications inside Docker containers, provides individual microservices with their own isolated workload environments, making them independently deployable and scalable. Learning about these technologies could widely benefit anyone who would like to venture into the world of cloud computing. This course is designed to give an introductory exposure to Docker and microservices. It is divided into three parts. The first part focuses on Docker, the second part focuses on Apache Juneau Microservices, the final part talks about how to integrate microservices and Docker, that is, run a microservice inside a Docker container. So here are the prerequisites for this course. The student would need some level of software engineering experience. He or she would also need to have Java knowledge. Basic microservices knowledge and knowledge of cloud computing terminologies are nice to have but not required. In addition to these, some basic level of Unix or Linux operating system exposure and any Java IDE experience, preferably Eclipse, is nice to have. In the first part of the course, we will talk about Docker. Docker is an open source project that automates the deployment of software applications inside containers by providing an additional layer of abstraction and automation of operating system level virtualization on Linux. You can consider this equivalent to a CD-ROM ISO image that is burnt onto an actual physical CD-ROM device. Just like CD-ROMs run ISO images, Docker containers run Docker images. Every Docker container runs a Docker image, which is a self-contained executable unit containing all that is needed for execution. Docker allows an application to execute within its own sandbox. It is a standardized package with all the dependencies that can be easily deployed. Docker uses a client-server architecture. The Docker client talks to the Docker daemon, which does the heavy lifting of building, running, and distributing your Docker containers. The Docker client and daemon can run on the same system, or you can connect a Docker client to a remote Docker daemon. The Docker client and daemon communicate using REST API over Unix sockets or a network interface. The Docker daemon listens for Docker API requests and manages Docker objects such as images, containers, networks, and volumes. A daemon can also communicate with other daemons to manage Docker services. The Docker client is the primary way that many Docker users interact with Docker. When you use commands such as docker run, the client sends these commands to dockerd, which carries them out. The Docker command uses the Docker API. The Docker client can communicate with more than one daemon. Next, we'll talk about some of the important Docker concepts. A Docker registry stores Docker images. Docker Hub is a public registry that anyone can use, and Docker is configured to look for images on Docker Hub by default. You can even run your own private registry. If you use Docker Data Center, it includes Docker Trusted Registry. When you use the Docker pull or Docker run commands, the required images are pulled from your configured registry. When you use the Docker push command, your image is pushed into the configured registry. Docker images are read-only templates with instructions to create a Docker container. Docker image can be pulled from a Docker hub and used as it is, or you can add additional instructions to the base image and create a new and modified Docker image. After you run a Docker image, it creates a Docker container. All the applications and their environment run inside this container. You can use Docker API or CLI, that is a command line interface, to start, stop, and delete a Docker container. Next, we will see how to install Docker in your Windows machine. Usually Docker is installed on Unix or Linux machines because that's where our containers run most of the time. But for the purposes of this training, we'll try to install it on our Windows machine. So first step is you have to download Docker from the official Docker website. Then you have to double click on the installer, and which is like any typical Windows installer, and install the Docker software. And then when you click finish, Docker starts automatically, which is a service, and Docker loads a welcome window giving you tips to access the Docker documentation. So let us try that now as a practical demo. So let us go to the official Docker download page. You can see that the Docker installation file is being downloaded. And once it's downloaded, let's try to install it. And I accept, install it. Let's click finish. So Docker needs this Hyper-V feature on Windows 10 to be enabled for it to work. So let's enable it and it will restart my computer. So let's wait for that. So now my computer has restarted, and you can see that there is this icon on my desktop that says Docker for Windows. When you double click it, this will start the Docker service, and then you can go to PowerShell. This is going to be our Docker command line, so you can run Docker commands from here. So these are the most commonly used Docker commands. I will be attaching a link to this presentation for all of you to try these out. Let's try some of these commands as part of our Hello World application. So this is the first sample application that we are going to try. We'll be mainly running two commands, the Docker run and Docker images, as shown in the slide. So let's try running these on the PowerShell command line. So this is our PowerShell command line where we have installed Docker. So let's try to do Docker run. So if you see the steps that are being executed, when I do Docker run hello world, it's first says it's unable to find the image hello world locally. So because it's not there locally, it tries to pull from the Docker registry, that is the Docker hub, the default Docker registry available. Then it says pull complete, and then it says the status is downloaded newer image for hello world latest. So this latest here, anything after this colon is called the tag. So this is the name of the image and latest is the tag. You can have multiple tags under the same image. So you can see that it has run the image, and the image actually does nothing but print this message, this whole message. This entire thing is coming from the Docker image for hello world. Now since Docker has pulled this image into our local registry, let's try to do Docker images. You can see that the repository is hello world, the tag is latest. Every image has an image ID and when the image was actually created and the size of the image. So now this image has been downloaded in the local, and next time when you run hello world using Docker run, it will not try to pull the image from the repository because it's already been downloaded and it's available locally. So this completes our first Docker application, the hello world application. And let's move on to microservices. Now that we have a good introduction about Docker, our next topic would be microservices. What are microservices? The microservice architecture is an architectural style that structures an application as a collection of services that are highly maintainable and testable, loosely coupled, independently deployable, and organized around business capabilities. You can also say that it's a distinctive method of developing software systems that tries to focus on building single function modules with well-defined interfaces and operations. Or, in very simple words, microservices are a design pattern for breaking down large architectures into small independent services. The microservices architecture consists of a collection of small autonomous services. Each service is self-contained and should implement a single business functionality. In the diagram, you can see two different types of architectures, monolithic and microservice. Unlike microservices, a monolith application is built as a single autonomous unit. This makes changes to the application slow as it affects the entire system. A modification made to a small section of the code might require building and deploying an entirely new version of the software. Scaling specific functions of an application also means you must scale the entire application. Microservices solve these challenges of monolithic systems by being as modular as possible. In the simplest form, they help build an application as a suite of small services, each running in its own process and are independently deployable. These services may be written in different programming languages and may use different data storage techniques. Microservices are often connected via APIs and can leverage many of the same tools and solutions that have grown in the RESTful and web service ecosystem. Microservices offer several advantages. The first one is agility. Because microservices are deployed independently, it is easier to manage bug fixes and feature releases. Say, one part of the application needs a rollout as a result of a bug fix release. It would be easier to provide a release for that specific part, which is written as a microservice, rather than providing a major release for the whole product for a simple bug fix. Second, a microservice should be small enough that a single feature team can build, test, and deploy it. Small team sizes promote greater agility and improve the team velocity and focus. Third, teams can pick the technology that best fits their service, using a mix of technology stacks as appropriate. All these technologies will be connected using a common interface such as REST. This also enables a team to take advantages that different technologies have to offer for their use case. Finally, services can be scaled independently, letting you scale out subsystems that require more resources without scaling out the entire application. For example, if a web application has the greatest number of hits on a specific page, the microservice backing that page can be scaled to handle the load, and the entire web application need not be scaled. There are several frameworks available out there to create microservices using different programming languages such as Java, Python, and others. For this course, we will be focusing on Java, specifically the Apache Juneau framework. Apache Juneau is a single cohesive Java ecosystem consisting of the following libraries for different purposes. We have a library for marshalling POJOs, a REST server and a REST client, a server specifically designed for Spring Boot microservices, a library for creating microservices in general, and we will be focusing on creating microservices and running them on a Jetty server, which is the last one listed here. This includes a REST microservice API that combines all the features above as a simple configurable Jetty server for creating lightweight standalone REST interfaces that start up in milliseconds. The Juno microservice Jetty is an API for creating standalone executable jars that can be used to start lightweight configurable REST interfaces with all the power of a Juno REST server and client APIs. To use this library, you need to add this Maven dependency to your project's pom.xml. If you're not using Maven, then you need to manually import a bunch of libraries or jars, which we won't be doing since Maven is far more simpler. Now let's create a sample application using Eclipse IDE for Java developers. This is the Eclipse project structure of the sample project, and we will be downloading the sample project directly from the Apache Juneau website to get the hang of the overall structure and what needs to be done to get a Jetty server up and running with Apache Juneau. This is the main class that is going to create an instance of the microservice. Now let's do a practical demo and create an actual microservice using Eclipse, and then we'll get to know more about how to create an instance. Now let's create a sample project using Eclipse IDE. So before we do that, we have to download the libraries or the sample project from the Apache Juneau website. So let's go to the website. You have this link called downloads. In the downloads, we are going to download the version 8.1.3, which is the latest version. If you go to the binaries link, you'll get a list of URLs or mirrors from where you can download the zip file. You can see that it's been downloaded. So let me go to my downloads folder. So here is the file. So let me unzip it. In the same folder. So just for convenience, let me copy and paste it in a new folder. In my desktop. So inside this folder, you'll have a bunch of other subfolders. You'll have the Juno jar, but the folder that we are interested in is the projects. So if you see, Juno comes with a list of sample projects. You can you can use any one of these projects, but for our course, we'll be using the MyJetty microservice project. We'll be importing this project into Eclipse, and we'll see how it looks. So let's start up Eclipse and import this project. So now let's open the Eclipse IDE. We'll be importing the sample projects onto Eclipse IDE. So let's open a workspace. You can have any name. It'll just create the folder for you. So this is my workspace. What I'm going to do is go to File, Import, under General, select Existing Projects into Workspace, click Next, select the Archive File radio button, go to Browse, and you might have to navigate into the folder where you downloaded your Juno zips, and then let's select MyJetty microservice under projects, and then click on finish. So this project is being loaded onto the Eclipse workspace. So the project has been loaded successfully. So there are a couple of files that we have to look for. So this is the main class where the instance of the Jetty microservice is actually created. So this is how you create it. So it's Jetty microservice.create, which creates an instance, and then if you have any arguments you can pass, and this is the servlet, which is going to get loaded when the microservice is loading and the server is starting. So we'll open root resources and see shortly what's in there, and then build, start console, and join. So since this is the main entry point for the microservice, let's see what's in root resources.java. Yeah, so this is the root resources.java. So what we see here is an endpoint, the path where this microservice is going to be hosted. And then it has a couple of children classes. So one is hello world resource, config resource, log resource, and debug resource. The last three, the config resource, log resource, and debug resources, are coming out of the box from the JT microservice jar. So it's part of the whole Apache Juneau framework. We'll see how these three look like when we actually run the microservice. And our main class where we are going to have our business logic is this hello world resource.class. So if you have any other Java file that you have your business logic to be hosted, you can list them under children here. And yeah, so let's open the main class hello world resource.java and see what it looks like. So we have to remember that the endpoint starts at slash, and then under hello world resource you'll have the rest resource path. So it's like slash hello world is where this hello world resource will be hosted. Slash config is where the config resource will be hosted. Slash logs is where the logs resource will be hosted, and slash debug is where debug resource. But the last three are there directly in the Juno library, so we don't need to do anything for that. This is the one that we created, so we are hosting the microservice under slash hello world endpoint. So the class, a simple class, just looks like this, like any other REST web service. So it's public class hello world resource extends basic REST servlet, and then we have this REST method annotation, which actually specifies the HTTP method and the path. So this method is annotated with this REST method annotation, and it just says nothing but just returns a simple string that says hello world. So if we have multiple methods, we can do multiple things. So this is the main thing that we have to note here is this @rest annotation and the @rest method annotations, which are the most important ones. So this method will be hosted under slash hello world endpoint because the path is slash. Say we have another method, say get path, instead of star I'll say get path of test, and say hello test, and then say maybe return another string. So this method is hosted under the endpoint slash hello world slash test, and this method is directly hosted under slash hello world. So for now, let's comment out this and see how this microservice behaves. So let me put the star back here like it was before and see how it actually behaves out of the box. So this sample project also has a Eclipse launch file that is predefined with what to do when launching the microservice. So to run this microservice, what we need to do is just right click on the launch file, do run as, and my JT microservice. So if you look at the console, it says logging initialized and server started on port 10,000. So now let's go open https localhost 10,000. So you can see that the microservice is here, and we have all the 4 resources that we listed in our root resources. So we have hello world, config, log, and debug, and all of them have been loaded here: hello world, config, logs, and debug. So let's go to our hello world resource. So let's see what is displayed here. You can see that under slash hello world endpoint, which is the endpoint that has been specified here, and since the path is given as /star. This method is invoked and we are just returning the string hello world. Now when you go back, go to config. So this is the configuration file for the JT microservice. So this is being loaded from this file, myjtmicroservice.cfg. So every microservice, every Juno microservice has a config file which it actually loads. If you see this line here, running class and using config file myjtmicroservice.cfg. So this config file is very important because it holds the main configuration for the whole microservice. It just has a couple of general stuff like the theme, header, footer, the appearance, the logger settings, what is the log directory, what is the format of the log file that is to be generated. So if you see, the log file here is microservice %g.log. So if you go up and go to the logs resource, your log file name format is microservice.0.log. So that's what this format says. And then the date format, and you can configure different logging levels. You can configure the console levels and some of the system properties as well. So it's basically the configuration file for the whole microservice, and which you can also view from the endpoint using the /config endpoint, and then you can view logs using the /logs endpoint. If you look at this view, there are no logs as of now. The microservice is not doing anything. And if you go to debug, this is JT thread dump. If there is a problem, you can always go here and see what's going on. And this is our endpoint. Now let's try to add our own endpoint. So I've stopped the server here, and let's uncomment this new REST method that we had added for /test endpoint, and let's remove the star here. So we have two REST methods, each doing different things at different endpoints. So let's run this again. Run as myJT microservice. So it says server started on port 10,000. Now let's refresh this page. So the server has loaded. Now the hello world endpoint displays hello world, which is as expected the first REST method. And to test the second REST method, let's do /hello world/test. So you can see that the second REST method is run and the hello world test has been returned. So this is how you can actually create multiple methods with different endpoints and perform different business logics in each of them. Now that we have a basic introduction of Docker and Apache Juneau Microservices, next we'll focus on how to deploy microservice into a Docker container. As part of that, we'll learn how to create a Docker file. We'll also understand the Docker file instructions and some of the commonly used instructions such as entry point, cmd, copy, and add. Then we'll look at how to deploy the Juneau microservice into a Docker container by building our own Docker file. And then we'll see how to make changes to the image and viewing the container logs, and also we'll look at how to view the exited containers. So what is a Docker file? A Docker file is a text file that has a series of instructions on how to build your image. So you can create a Docker file with the required instructions, and once that is ready, you will use the docker build command to create a Docker image based on the Docker file that you created in the previous step. And once this is done, you can use the docker run command to actually run the image and see the output. Now let's see a practical demo of how we can create a Docker file. So we'll start with a simple Docker file and see how to run it. So now let's see how to create a Docker file. So let me create a new folder that will store my Docker file, and inside this folder let me create a new file that's called Docker file. So any file that has a set of instructions should be called a Docker file, and every image will have one Docker file per image, which will contain all the instructions, and the name should be Docker file, it cannot be anything else. So let me open it with Notepad, and we are going to add our instructions here. So let's start with basic set of instructions. Say from busybox latest. So this from keyword is used to specify the base image. Busybox is a base Linux image that has minimal installation, and we're going to use that as a base image for our container. So our containers operating system is going to be based on this image. And then let us do a simple command that actually prints the Unix date onto the console. So we have two simple instructions here. From indicates the base image that has to be used, and cmd indicates the command that has to be run when we run the container using the docker run command. So let me save this, and let me go to my PowerShell. So let me go into my folder. Oh, it's already there. Okay. And let me do a docker build -t my image latest and a dot. So docker build is the command for building the docker image, and -t specifies the tag. This is going to be my image name, this is going to be my image tag, and there's a dot in the end. It says the docker file that has to be used for building this image is in the same directory as the present working directory. So let me press enter. Yeah, you can see that it's pulling the busybox latest base image, and then the second step is it's trying to run the command date, and both these instructions have now been embedded into the docker image, and finally says successfully built this image. So let us see the image that we built here. So we have three images: the hello world one, which we created earlier, then we have busybox, which is going to be our base image, which has been pulled, and then we have our custom image, the my image latest tag, which we just built now using the docker build command. So now that we have the image ready, our custom image, we can run the image using the docker run command. So let me do a docker run my image and the tag. See, you can see that the date has been printed. Whatever is specified under the cmd command will actually be executed when you do the docker run on your image. So let's look at some of the most commonly used docker commands in a docker file. The entry point, copy, and add. An entry point actually allows you to configure a container that will run as an executable. We'll see an example next. The copy instruction copies new files or directories from source, the folder, and adds them to the file system of the container at the path destination. So if you specify a path, then the source file will be copied over to the path inside the container. The add instruction also copies new files and directories, but it has an additional capability of downloading remote file URLs from source and adds them to the file system of the image at the path specified by the destination. So we'll see an example for these in the next slide. So this is a little more complex example of a Docker file. Uh, we know the from keyword, which is used to load the base image. In this case, the base image is Ubuntu. Then we have a couple of run commands that actually run the command inside the container. So we are going to do an apt get update, an apt get install nginx. So we are going to install an nginx server and get it up and running. So we run these two commands using the run command in the Docker file. And then what we're going to do is we're going to copy a local file, that is the index.html, onto the Docker containers file system under user share nginx html. So this user share nginx html is a path inside the Docker container where the file will be copied to. And then we have the entry point command that actually starts the nginx server using a couple of parameters. So user has been nginx is the command, and -g and daemon of are the extra parameters. Then we have the next instruction, which is called expose, and it says 80. It means that we are going to expose the port 80 inside the Docker container outside so that we can access the service running on that port. So we are exposing the port 80 inside the Docker container to the external world. And then we are going to run this Docker file using this docker run command, which is actually a little more complex than the one that we saw earlier. The -p is 80:80 is tells the Docker to map the ports exposed in the container to the specified port on the Docker host. The first parameter specifies the port in the Docker host, and the second parameter is mapped to the port exposed in the container. And web server is the name of the created container based on the nginx image, and my image is the name of the image that we have actually created. So now let's update our Docker file with the new set of instructions. I have already done that here. This is going to run an nginx container. It's going to use the Ubuntu base image, and it's going to install nginx in the container, and it's going to start it up. So let's try to build this new Docker file. So let's do a docker build -t my image latest and dot. This is going to pull the Ubuntu image. It's going to build our Docker file. Yeah, now it says it successfully built the image. Now we are going to see that this image is there. So now let's update our Docker file with the new set of instructions. I have already done that here. This is going to run an nginx container. It's going to use the Ubuntu base image, and it's going to install nginx in the container, and it's going to start it up. So let's try to build this new Docker file. So let's do a docker build -t my image latest and dot. This is going to pull the Ubuntu image. It's going to build our Docker file. Yeah. Now it says, now that we have created a Docker image and we have our running container, let's see how to push that image into the Docker Hub registry. This basically involves three steps. The first one is to log into the Docker Hub. The second one is to tag the image ID with a meaningful name and a tag, and then push the image into the Docker Hub registry. So let's see how we can push our new Nginx image into the Docker Hub registry. So now let's see how to push the Docker image from our local into the Docker Hub registry. So the first step is you have to create an account at hub.docker.com. You can create a free account using the username and password, and you will use that to log into the Docker Hub registry. So let's first do a Docker login. So use your username and password that you have created at hub.docker.com. So we have logged in now. So let's see what images we have in our registry. So the one that we are interested in is the my image latest that we have tested by installing an Nginx server and starting up the container. So we'll try to push this image into the repository. So let's first tag this image into a meaningful name. So you can run docker tag the image ID, and then you can use your user ID that you use for login, because by default a repository will be created using your user ID at hub.docker.com, and then you can give a name for the image, say Nginx test, and then you can say version 1 as the tag. So let's tag it. So now when you run docker images again, you can see that the new image has been created with a new tag, but the image ID is same as. So now let's see how to push the Docker image from our local into the Docker Hub registry. So the first step is you have to create an account at hub.docker.com. You can create a free account using the username and password, and you will use that to log into the Docker Hub registry. So let's first do a Docker login. So use your username and password that you have created at hub.docker.com. So we have logged in now. So let's see what images we have in our registry. So the one that we are interested in is the my image latest that we have tested by installing an Nginx server and starting up the container. So we'll try to push this image into the repository. So let's first tag this image into a meaningful name. So you can run docker tag the image ID, and then you can use your user ID that you use for login, because by default a repository will be created using your user ID at hub.docker.com, and then you can give a name for the image, say Nginx test, and then you can say version 1 as the tag. So let's tag it. So now when you run docker images again, you can see that the new image has been created with a new tag. So up until this point, we are now familiar with Apache Juneau Microservice, how to create a microservice and run it. And also we know the Docker container basics, how to deploy an application in a Docker container and how to write Docker files. So now let's combine both of them. Let's try to deploy a Juneau microservice inside a Docker container. So the following are the steps to achieve that. So first step is you have to create a Docker file for your microservice, and the next step is to create a jar file for the Eclipse project that contains a microservice. The third step is to copy the necessary files into the same folder which contains a Docker file, so that when you run the Docker build, all the necessary files will be copied over to the container. And then finally we run the Docker build and the Docker run commands to actually run the microservice from within the container. So let's see a practical example of how to do that. So this is our JT microservice project that we had created earlier in Eclipse, and we were able to run this using this launch file from within Eclipse, and we opened the microservice homepage and we saw that the microservice was up and running. So what we're going to do now is to create a jar of this microservice and create a Docker file for running the jar and run the container within our local machine. So what we have to do is first right click on the project, and do Maven, do run Maven install. What this is going to do is it's going to generate a jar file, and the jar file will be available inside this target folder for our microservice. So let's wait for the build to complete. Yeah. So we have a Jetty microservice jar. We have a Jetty microservice jar and we have a Jetty microservice config file. So these two files are needed to get our jar up and running. So let's copy these two files into the same folder where we have our Docker file. So this is the old one, we can ignore it for now. Let's see how we are going to write the new Docker file. So we have the set of commands. The first one is from Java 8. So we have a base image that has Java already installed on it. Then this work directory, work dir is another instruction, another Docker instruction. It just sets the root directory to the directory that we specify as the argument. Right now it's just the main directory /. And the next instruction is add. We are adding the jar into the container with the same name and inside this directory. And then we are also adding the config file for the Jetty microservice into the container with the same file, and this file will be available in the container under /myjettymicroservice.cfg. And then we have this expose port number. Since our container is going to run microservice in, so this is our Jetty microservice project that we had created earlier in Eclipse, and we were able to run this using this launch file from within Eclipse, and we opened the microservice homepage and we saw that the microservice was up and running. So what we're going to do now is to create a jar of this microservice and create a Docker file for running the jar and run the container within our local machine. So what we have to do is first right click on the project, and do Maven, do run Maven install. What this is going to do is it's going to generate a jar file, and the jar file will be available inside this target folder for our microservice. So let's wait for the build to complete. Yeah. So we have a Jetty microservice jar. We have a Jetty microservice jar and we have a Jetty microservice config file. So these two files are needed to get our jar up and running. So let's copy these two files into the same folder where we have our Docker file. So this is the old one, we can ignore it for now. Let's see how we are going to write the new Docker file. So we have the set of commands. The first one is from Java 8. So we have a base image that has Java already installed on it. Then this work directory, work dir is another instruction, another Docker instruction. It just sets the root directory to the directory that we specify as the argument. Right now it's just the main directory /. And the next instruction is add. We are adding the jar into the container with the same name and inside this directory. And then we are also adding the config file for the Jetty microservice into the container with the same file, and this file will be available in the container under /myjettymicroservice.cfg. And then we have this expose port number. Since our container is going to, I would also like to provide some additional information on some of the additional actions that you can do with the Docker images and the containers. You can make a changes to the Docker image. I'll also show you how to stop and remove a container, how to remove an image, and how to view exited containers. So removing an image is very important because some images are very huge and they might take up the disk space. So it's a good practice to remove an unused image at any point of time. So let's see how to do all these steps. So let's go back to our previous screen where we had this Juneau microservice up and running. So the first thing is, how do you make changes to a Docker image? So first thing is, you can either create a copy of that image using a new tag by building it with a new tag, or you can replace the existing image. So say you change something in the Docker file here. Say you change the port from 10,000 to 20,000 and you want to build the image again. So what you have to do is you have to just run the docker build command again and use the same tag as what you've used before, and this image will be overwritten with your changes. So if you don't want to overwrite this, just give a different tag. Even though the name of the image is the same, just you can call the tag as latest one, and it will create a new version of the image and the old image will still be there. So in either case, any change to your Docker file, you can use docker build and you can test your changes against the new image. And the second aspect that we're going to see is how to stop and remove a container. So let me show you. So let's just check the list of running containers. We use docker ps. We see that this container is up and running. So without removing this container, you cannot remove the image. So first step is to remove the container. So to remove the container, you can just run docker rm and you can give the container ID. But then this will not work, but I'll tell you why. Yeah, you cannot remove a container that is actually running. So the first thing you have to do is you have to stop the container. So to stop the container, you can use docker stop and the same container ID. It will take a while, but eventually it will stop. So let's go back to our previous screen where we had this Juneau microservice up and running. So the first thing is, how do you make changes to a Docker image? So first thing is, you can either create a copy of that image using a new tag by building it with a new tag, or you can replace the existing image. So say you change something in the Docker file here. Say you change the port from 10,000 to 20,000 and you want to build the image again. So what you have to do is you have to just run the docker build command again and use the same tag as what you've used before, and this image will be overwritten with your changes. So if you don't want to overwrite this, just give a different tag. Even though the name of the image is the same, just you can call the tag as latest one, and it will create a new version of the image and the old image will still be there. So in either case, any change to your Docker file, you can use docker build and you can test your changes against the new image. And the second aspect that we're going to see is how to stop and remove a container. So let me show you. So let's just check the list of running containers. We use docker ps. We see that this container is up and running. So without removing this container, you cannot remove the image. So first step is to remove the container. So to remove the container, you can just run docker rm and you can give the container ID. But then this will not work, but I'll tell you why. Yeah, you cannot remove a container that is actually running. So the first thing you have to do is you have to stop the container. So to stop the container, you can use docker stop and the same container ID. It will take. Now we are moving on to the final section of our course, which is about Docker monitoring. So first of all, why do we need to monitor our Docker containers? It is obvious that monitoring is an essential part of Docker-based environments. The essence of monitoring philosophy is to ensure that a running program or process is performing to the expected level. The main points that we are going to highlight are detecting issues and troubles at an early stage to avoid risks at a production level. Changes and upgrades can be done safely as the whole environment is tracked, and we can refine applications for better performance and robustness. We will look at some of the tools that are useful for monitoring Docker containers. The first of those is Docker Stats. So let's start with the simple monitoring tool provided by Docker itself as an API already included in the Docker Engine client, which is the Docker Stats command line. Docker Stats provides an overview of some metrics we need to collect to ensure the basic monitoring function of Docker containers. This API gives us an access to the CPU usage, memory, networking, information, and disk utilization for running Docker containers. It is about displaying a live stream of a container's resource usage statistics. To see statistics related to a running Docker container, we can simply run Docker stats with the desired options associated with the name of the container. If there is no name, Docker stats as default shows all the existing containers and its statistics. To use Docker stats, we simply write on the command line saying docker space stats. So the Docker stats shows the percentage of CPU utilization for each container and a lot of other details. So let's run Docker stats in our environment and see what it shows. So let's run Docker stats command in our Docker environment. You can see the CPU usage percentage, the memory usage, the memory limit, memory percentage, the net IO and the block IO, and the PIDs. So this is kind of a live data that gets updated. So let's run Docker stats command in our Docker environment. You can see the CPU usage percentage, the memory usage, the memory limit, memory percentage, the net IO and the block IO, and the PIDs. So this is kind of a live data that gets updated. Another important monitoring tool for Docker containers is Prometheus. It is an open source toolkit used for monitoring and alerting. Prometheus can be used to monitor computer systems and alert system admins about the health of your environment. To understand how Prometheus works, we have to look at it as a self-hosted set of tools that provide metric storage, visualization, alerting, and aggregation. We call these metrics providers, exporters. There are also libraries that can be used to create custom exporter. When it comes to Docker, Prometheus needs a container exporter that will capture metrics and collect data so that it can be analyzed later. Whenever our exporters are running, we can launch the Prometheus server based on a configuration file that tells the server from where the metrics can be scrapped. Once the metrics endpoints are integrated into the time series database, the rest of the Prometheus monitoring toolset can be used to observe metrics and raise alerts if something is underperforming. Related metrics and graphs are displayed in a UI dashboard based on the Grafana toolkit as shown in the diagram here. So if we are comparing this monitoring tool to other ones, we will conclude that the Prometheus is a powerful tool with a competitive UI and high analytical capabilities that necessitates an additional effort for deploying it and configuring its files. Another monitoring tool that can be used to monitor Docker is Dynatrace. Dynatrace provides a lot of metrics that include CPU usage, memory usage, the network traffic, and throttling. Throttling means total time that a container's CPU usage was actually throttled. Dynatrace automatically creates a complete real-time topology of your containerized microservice architecture. It discovers all your containers and what's running inside of them, and it knows when containers are spun up or down, so your topology is always up to date. Sysdig Cloud leverages open source Sysdig technology to provide a best-in-class Docker monitoring, analytics, alerting, and dashboarding for containerized environments. It also includes scheduling and orchestration tools that enable sophisticated and automated deployment of containers. At a high level, it is as simple as this. With Sysdig Cloud, you get full visibility inside every container across your entire operating environment. Again, all of this is achieved without needing to instrument your Docker containers or your application code. All you have to do is add the Sysdig Cloud container to your hosts, and with Sysdig Cloud, you can do things like monitoring Docker applications with no application monitoring plugins, collect service-oriented architecture data like top URLs, HTTP error codes, and database queries. And you can also automatically map the topology of your Docker environment to highlight dependencies and bottlenecks. And the main thing is you can alert based off of your application and service performance, not just container or host resource utilization, which is a tremendous advantage compared to the other monitoring tools that we discussed. The last Docker monitoring tool that we'll be discussing in our monitoring tools overview is Datadog. The simplest way to monitor Docker containers is to run the Datadog agent on the host, where it can access container statistics. This is especially true if you are deploying Docker on existing full-fledged host operating systems, along with existing applications such as databases. So, based on our research so far, we have multiple Docker monitoring tools. We still have more. This course actually covered an overview, a high-level overview of the main or most commonly used Docker monitoring tools. Uh, the tools are mainly used to give a more visual look to the performance of the Docker containers, and it will definitely be useful for large-scale applications that have multiple microservices running and hundreds of Docker containers running. So we have reached the end of our course. Just to summarize what we have learned so far, we initially learned containerization basics. We learned about the Docker client, the Docker commands, the Docker file, and running a Docker container. We also learned how to create a basic Apache Juneau microservice using the Apache Juneau library and a Jetty server. We also learned how to deploy the microservice in a Docker container and bring it up and running. And we saw different Docker commands to start, stop, kill a container, and remove an image and build an image. We also saw a high-level overview of different Docker monitoring tools that are available in the market, which can be useful to monitor the performance of our containers. So this concludes our course, and I hope it was useful and you all got to learn new stuff. Thank you again.